So for group homework number 3, for question 1, it says use the server given above to calculate the PI of polyglutamic peptide E. So I am typed in all 5 of the E's, and now I'm going to compute parameters. And over here, it gives the PI value of 3.51.
Okay, so I'm doing number 2, and it's going to ask about how do we decrease, essentially, the PI of a polyglutamic peptide by 1 unit using the EEE peptide sequence for glutamic acids. Like, how many glutamic acid residues would I need to add to decrease it by 1 unit? So we started off here with 3.51 units, so we're going to try to get to 2.51 units. And I have already computed it. And basically, if I add 81 of these E's, then essentially my PI, theoretical PI, will be 2.51. You see there it says number of acids, amino acids is 81 that were added, like I said, to get that theoretical PI of 2.51.
This is Drew Dixon solving questions 3 and 7 on homework 3. We're using the website XPC's protein parameters tool. In this question, we're trying to lower the PI to 2 units below its pentamerase form. So we're going from 3.51 to 1.51. And here we mostly just test out numbers until it works. Here we can see at 440 peptides, we get 1.8. So another set should put us in spot. And this came out to be approximately 860 residues.
So in this problem, we're given an amino acid sequence of what looks like arginine. Yes, arginine, with a given pKa. What we want to know is how many more arginine residues do we need to add to increase the pKa by 1 unit. Is it in units? 1 unit. So the amino acid sequence we're given is R, 6 arginines in a row. Our given pKa is 12.5. We want to know how many arginine residues to add to get an average pKa of 13.5. So to determine this new length, we use the formula N, which will be the number that we need of amino acid residues, is equal to the desired pKa minus the average pKa of the peptide we have now. I'll say peptide given. All over pKa of arginine. That's so not how you spell arginine. I think that's right. That looks right. So plug that in. N equals 13.5 minus 12.5 divided by 12.5. N equals 1 over 12.5, which is equal to 0.08, which is approximately 1. So we round it up to the nearest whole number. We have 6 plus 1, because we started off with 6 arginines here. So we say 6 plus 1, and that's going to give us 7, which means we need 7 residues to increase our pKa by 1 unit.
For group homework number 3, question number 6, which is the second question I'm doing. It's asking us to calculate the average net charge of this peptide, written out here, at pHs 8.3 and 12.5. And then it wants us to use the pKa values in this chart from the textbook to solve the problem. I already went out and had these relationships between pH and pKa, and I wrote down the charges that we had to have memorized for the ones that are acidic and then the ones that are basically charged. So first, we're just going to go through here and cross out all the ones that are not charged. So that's going to be A, T, I, M, M. E and D are charged. I and A are not. T also, again, is not charged. E is charged. L is charged. L is not charged, but Y is. So we have these 1, 2, 3, 4, 5. So how I usually like to write it out to organize when I'm calculating it is the pKa value here, and then the pH value right here, and then I'll go ahead and write out all those letters on the side. So first I'm going to go ahead and do the C terminal right here, and then I'm going to do C, E, D, E, Y, and then the N terminal. So for the first pH, we're going to do for 8.3. So at pH 8.3, I'm just going to go ahead and write it all the way down. Again, this is just a way for me to organize my own thoughts. So obviously people do it differently. But now I'm going to look at the textbook chart at the values of all the pKa's, and I'm just going to go ahead and write them down. So C terminal is 2, C is 8.3, E is 4.2, D is 3.9, E is 4.2, Y is 10.1, and this is going to be 9. So now I'm going to do a little compare-contrast sign. pH is greater, equal, greater, greater, greater. This pKa is greater, and then pKa is greater here. I'm just going to go ahead and disregard those because usually between pH values between 2 to 12, the C and N terminals tend to cancel out, or they always have canceled out. So I'm not going to worry about calculating that. But now we're going to see which is going to be acidic and basic. At this value, it's just equal. And then at E, this is going to be basic since the pH is greater than the pKa. And it's going to be basic here again. It's going to be basic since the pH is greater. And then here, pKa is greater than pH, so that means this is going to be acidic. So now I'll just look at the charges on the charts here and correlate the letters to... So see here, it says E is basic. So I'll look here, and then basic charge, it's -1. So the charge of E will be -1. And so I'll just correlate the rest of the charges like that. And then, since in this case, for C, 8.3 equals 8.3, I just learned that's going to be 0.5 because it's just halfway in between 0 and the one charge that we could have. So total, when you add these charges all up together, it gives you -3.5 average net charge at pH 8.3. So that's our pH 8.3. Now we're going to repeat this process, but at pH 12.5. So I'm just going to quickly go ahead and write out the chart. C terminal E, C, E, D, E, Y, and then N terminal. And then we're going to do pKa and then pH. And so we have the pH is 12.5, so and then we have all the pKa's from earlier, so I'm just going to go ahead and quickly copy all those down. So now we'll just add in our compare-contrast signals. So this is how they all ended up turning out. And now we're going to look at the charges on this chart and correlate them with the letters. So these all look like they're going to be basic because the pH is greater than the pK in all of these. So now we're going to look at the basic charges. Okay, so when we sum all those together, we get -6 as the net average charge at pH of 12.5. And yeah, that's how we solve this problem.
The second question is asking us to consider the net charge of a protein. So we're given a protein in the worksheet, and we just sort of copy paste it over into the protein parameters tool, where we find that approximately 35% of the protein is arginine, a positively charged amino acid. This directs us to want to use a cation exchange column because of the negatively charged resin that can capture those positive charges.
This is Juliana Boyette solving number 8 and number 9 in homework 3. So number 8, all serine residues in the peptide can be phosphorylated. To purify the phosphorylated peptide, what type of ion exchange chromatography columns should be selected? Anion or cation exchangers? This is referring to the peptide in question 7. So if all of these serines were phosphorylated, it would essentially be giving each serine a negative charge, overall giving the peptide a negative charge. And in ion exchange chromatography, anion exchangers want to attract negatively charged peptides, and cation exchangers want to attract positively charged peptides. So in this case, since our peptide is phosphorylated, we want to use the anion exchangers. Question 9, how phosphorylation of serine will change the pK of arginine? Increase, decrease, or no change? So we have quite a few arginines in here, but there are quite a few serines phosphorylated as well. So if we look back in our notes, we know that near negative charge, the pKa will increase. So because all these serines are phosphorylated, the phosphate will give them a negative charge, and the negative charges being near the arginine will make the pKa of arginine increase. So they'll increase.